So, hi everyone. Today I'm going to talk about my research on this bilingual lexicon induction. This is a joint research between my work at BU and Chris Callison-Birch team at University of Pennsylvania. So to begin with, in starting when AI was first imagined, the quest has been for NLP is how we can build machines that understand this human language. So for example, given the sentence, the plane flies over the boat with a red bow, we want to be able to build an intelligent machine that can understand the meaning of the words, how the words relate to each other, how they relate to the real world, like what's possible, what's not, and to conclude, after doing some thinking, what the sentence actually means, that it's for the plane to fly over the boat whose front part is colored red and not the one carrying a big, red arc or some bow. So, but human languages, as it is very variable. You can express the same idea, the same meaning with many different ways and in many different languages. So given that we have more than 7,000 languages in the world, and only few have large enough annotated data for training NLP systems, the challenge now becomes how can we extend the coverage of current NLP systems to be able to cover other languages beside the high resource languages ones. So the frontier of this enterprise of trying to extend NLP to many different languages is machine translation. But state-of-the-art machine translation has still some way to go. So for example, here, for the sentence, the plane flies over the boat with a red bow, in English, it's actually translated to mean that thing, like the actually carrying some red bow, I guess, in Indonesian. Because Indonesian is not high resource languages, it's kind of medium resource, so there's not a lot of annotated data for it yet. So, and this gives rise to very funny pictures about incorrectly translated sentences. For example, here in Indonesian, memecahkan could mean solving, as if you are solving a puzzle or something. But in the context of shopping, like this is put up in a shop, it means breaking. So if you break something, you buy. But using Google Translate, you actually get, or Bing also, you get solving means buying. So, which is kind of funny. So traditionally, machine translation has relied on this typically large sentence-aligned bilingual text, where you have manually translated sentences from one language to another as your training data. But as mentioned, sufficient quantities for this parallel data is only available for a few language pairs, mostly Western language, Western European language. And we need actually about tens of millions words worth of these manually translated sentences to be able to train effective neural machine translation. And even then, even if we have this sufficiently large data, there might still be out of vocabulary words that we see during training, but we don't, that we see during testing, but we don't see during training. And getting manual translations are expensive. And even the dictionaries that we have for some languages are incomplete. And they look like this. So this is an actual Uyghur to English dictionary. As you can see, it's not machine readable, and it has more definition than translation. So even for us humans, it's not straightforward to use, let alone for a machine to use this. So the challenge then, again, how can we learn to translate with fewer labels? And this is the goal behind bilingual lexicon induction, which is how can we rely more on this cheaply attained, plentiful monolingual data and other resources, and reduce dependence on this bilingual data in order to produce word-to-word translations. So the idea goes back to the late 90s that we can, in fact, find word-to-word translations, even without parallel data, using the idea of context similarity. That words appear in similar contexts, no matter what language it is. So you can imagine, for example, for this foreign word tidur, you can get the context of that word, meaning the other foreign words that appear surrounding the word. And then you can use some C dictionary to project the context word in Indonesian to the context words in English. And once you get this projected vector, you can compare this projected Indonesian word to the other English vectors and get the translation. So currently, since there's more advances in learning word representations, instead of the sparse vectors that we've seen before, we can now get a more dense vectors to represent words. Similarly, as before, words that are similar will have similar vectors. And if you project them into the vector space, you can see that, for example, great and awesome, they are close together in the vector space. So more recently, there's also a discovery that when you plot these word vectors in different languages, whether English or Spanish, they have similar geometric arrangements, which means the relative positions of the words in English, for example, the word 4 and 5, their relative positions to each other is similar, whether in English or in Spanish. So with this in mind, you can imagine that we can learn a mapping from one language space to another. And that's how more works come up on this idea of creating this bilingual space where words from different languages, if they are similar, end up closer together in the bilingual space. So the idea is similar as before. You start from monolingual word vectors that you train on separate monolingual data of here, the foreign language Indonesian and the English word vectors. And then you use some C dictionary to learn the mapping function W, that when you apply this W to the vectors of the words from the source language in your dictionary, you get the vectors of their translations in your target language. And then once you learn this mapping W, given any source word that you haven't seen before in your C dictionary, you can get this projection to your target language space, and then you can do the same, compare with other vectors to get the candidate translations. And this kind of linear mapping does pretty well on closely related languages like English and Spanish, but as you can see, they don't do as well for distant languages like Czech to English or Vietnamese to English. And they also depend on the size of the monolingual data. So as you can see, if you want to have good word-to-word translations, you still need to have huge monolingual corpus. So the work that we did is trying to tackle these issues, for example, for distant languages by introducing nonlinear mapping. So we can learn nonlinear mapping W that takes into account these nonlinear functions to map from one vector space, the foreign vector space, to the English vector space, and vice versa. And for the lack of monolingual text, we can add other sources to measure translation similarities, like using related languages or using images. So for example, using related languages, you can imagine in Wikipedia, if you have a source word in the low resource language, like Uyghur, for example, here, you can find its translation to a related language using Wikipedia, for example, to Uzbek, which is very related to Uyghur. They're written in different scripts, but actually they are almost kind of similar language. But Uzbek is higher resource. So since it's higher resource, then it's easier then for you to pivot from Uyghur to Uzbek to English than going directly from Uyghur to English. So, and then the same idea can be applied to images. If we look at the images, even in Wikipedia of these words, we can see that you can see similarities between images of the same words that mean the same, in this case mean horse, in Uyghur, in Turkish, and in English. So you can use images to bridge the translation from your foreign language to your target language. Oh, I think it disappears. It's supposed to have picture. Oh, I think the picture disappeared, so maybe I...
Is this where you were?
Yeah.
Oh, the picture in here.
Yeah, it's actually in the PowerPoint, but in Google Drive.
Maybe it wasn't there.
Yeah. Okay, so I think it's here. Sorry about that. Oops, it's not here either. Oh no. Okay.
You're gonna stick with this one?
Nope, I need the pictures, otherwise it's not working. So, how can I do this? Do you have the email that I sent?
I can go check.
Or I just take my computer?
Yeah.
Yeah. Sorry.
No worries. It's coming, yeah. There you go.
Yeah. So the same way we can use then images to bridge translation between languages, because similar words in different languages have similar images. So we can identify translations via images who have high degree of visual similarities. But however, this doesn't always work, as you can imagine. For like very abstract word like concept, which means concept actually in English, if you take a look at the pictures, the images of concept is very varied, and it's hard to find the actual translation from images. So because concreteness of the word matters, what we did is we take the pictures of the foreign word, and we predict its concreteness measure. And then using this concreteness measure, we combine it with the image similarity plus the context similarity that I mentioned before, and using related languages to actually get better candidate translations. So now the question becomes like, how do we combine all these different signals for translations? So one idea that we had is to frame this translation as matrix completion. Specifically, we can formulate a matrix with the source words in the column and the target words in the row. And then we observe some initial translations, for example, from Wikipedia interlingual links. And then we use these observed translations to infer the unobserved slots in the matrix. So in this case, using Dutch as a related language, we can go from the English word fridge to the Indonesian word kulkas. But then matrix completion suffers from the cold start issues, where you have word that completely doesn't have any observed translations, for example. And then for these cold words, we use our bilingual word vectors to compute the potential translations. So in this way, we can alleviate the cold start issues by using other signals of translation similarities. And then in the experiments, we could back off to these noisier signals of translations as we encounter cold words. So we can start from this matrix completion using related languages, and then if it's cold words, we can back off to using the contextual similarity. And then you can imagine we can add more things like image similarity, and then transliteration, for example, for words that are simply written in different scripts. So we ran this experiment across many languages, from low resource to high resource languages. As you can see in the experiment, this is the accuracy at 10 of the word-to-word translations. That means the right translation can be found in the top 10 of your output. And you can see, like, for a different family of languages, using nonlinear mapping can actually improve significantly your word-to-word translations over just using linear mapping. But for the same family, it doesn't really make a lot of difference. And then you can also see that we still suffer from having not enough text, because Wikipedia, for example, only has less than 1 million documents written in Somali. So when there's not enough text, we still suffer in terms of our performance. And this is where images come in. When there's not enough text, we can use images to help us translate. And we run the experiment using both, the image similarity concreteness and the text similarity across languages. And we see that across languages, from low resource to high resource languages, combining text and images and concreteness improves the performance of the word-to-word translation. And particularly, it improves the concreteness matters more for high resource languages, because in high resource languages, you have a lot of text. So the signals that come from text is strong enough, and you only want to use the signals that come from images when the image, the word is very concrete, right? And then we actually released this massively multilingual image dataset that we use for the experiments. It contains images from 100 languages and their English translations, and it has up to 10,000 words per language and up to 100 images per word. So this is, we believe this is by far the largest data set of its kind. And we also experiment further with using transliteration, because oftentimes names or rare words are just written in different scripts in different languages. So when we add this to text translations, it actually improves the performance for translating names and other rare words, because using text alone, you get related names but incorrect names. And we can see also that the improvement is more when you are at the low resource languages zone. So in current work, we are extending more this idea of learning this multimodal, multilingual representation. For example, by extending our massively multilingual image data sets to cover images of more words. So you can imagine we can use weak supervision in terms of noisy captions of images to learn images of new objects that we've never seen before in our data set over time. And then we are also using this better multimodal, multilingual representation to develop tools for analyzing public communication in many languages. So basically combining images and text to understand the framing of the media, like whether they mean, when they give certain images and text, whether they mean peaceful demonstration versus angry protesters. So that's the current work we are doing right now. So thank you.